So welcome everyone to this week's One World IMP Mathematical Physics seminar. So for those of you who are joining us for the first time, this is the regular seminar of IMP, International Association of Mathematical Physics. And if you want to find out about our series, here is a link. And you can also join our mailing list to find out about our seminars. And this seminar, as usual, is going to be recorded, and you can watch it on our YouTube channel. Okay, so let's get to the talk. It's my great pleasure to introduce Karol Kozlowski, who is going to talk about exact rigorous construction of the Sinh-Gordon quantum field theory in 1+1 dimension. So please, the floor is yours.
Thank you very much, Kasia, for the introduction, and I'd like to thank the organizers of this One World Mathematical Physics seminar for the invitation and the possibility to present some aspects of my work here. So what I want to talk about is about a route which allows one to rigorously construct a specific 1+1 dimensional quantum field theory, which is called the Sinh-Gordon model. Typically, when one would think about constructing quantum field theory, one could choose to take the constructive path integral approach and try to do something with that. Quite a deal of results is possible in this approach, but very often they are not exactly very explicit. And the situation is a bit better in 1+1 dimension, because some cases you can rely on integrability, and there you can choose a completely different path to construct a theory, which is called the bootstrap program. So this talk will be discussing this bootstrap program approach, and in particular how it allows one to construct a theory, and what has already been done and what still remains to be done to get a full construction. And the main advantage of this approach, say in respect to the path integral approach, is that one is able to obtain fully explicit, exact expressions for multi-point correlation functions in this theory, and this opens towards many applications, like studying universality properties of those objects through their explicit expressions. So I will first try to start the talk by trying to give you a brief description of the overall setting in which the bootstrap approach fits in. What kind of object one needs to construct to kind of follow the recipe of the bootstrap approach. And then I will discuss the implementation of this program in the case of the 1+1 dimensional Sinh-Gordon model. And in particular, I will try to show you some formula one can provide within this method for the correlation functions, be it 2-point or multi-point correlation functions in this Sinh-Gordon quantum field theory. Now, the kind of once one gets to the expressions for the correlation functions, the last but technically not the least step in the whole approach is to prove the well-definiteness of these expressions. Simply because these expressions are given by certain series of multiple integrals, so a series where n summand is given by a n-fold integral, and one needs to prove the convergence of those series. So, to say things differently, control with sufficiently good precision the growth in n of certain n-fold integrals. And this was an open problem for a while in this setting. I managed to move the problem further, at least for certain cases of correlation functions. And basically, in that case, one can establish convergence of such expressions by pushing forward certain techniques which were fruitful in the study of certain classes of large random matrices. And this I will discuss in the third part of the talk. So, well, just to keep things up, well, first, if one starts with some classical field theory in 1+1 dimensions, so consider some scalar fields depending on the time and space variables, which satisfies a certain nonlinear partial differential equation. So D'Alembert operator acting on the field phi, and then some potential evaluated at the field phi, and all this equal to 0. So just as it was possible to quantize the classical equation, Newton equation of motion for systems with finite degrees of freedom, what one would like to achieve for such a partial differential equation is to produce a quantum counterpart of the classical field theory. This turned out to be, especially if one wants to do it rigorously, an extremely complicated problem. First of all, there were many advances on these questions on the formal physics sides, where people used formal path integration, formal renormalization to be able to produce objects of interest in this quantum field theory, in particular compute certain expansions in perturbations of the potential around the free case. But that was, it was astonishing how it was bringing correspondence with the experiments. But this was definitely not rigorous, but still the correspondence with the experimental data definitely indicates that there has to be some systematic way to make all these constructions rigorously. In general dimensions, there are possibilities of constructing quantum field theories, but still it's on certain case-by-case study. And maybe the situation is slightly better in one dimension because we can prove the existence of large class of quantum field theories by constructive renormalization techniques. Still, what I would like to stress is that mostly one deals with existence results, so that everything is well defined and the objects you want to physically study exist. But to have some more quantitative insight into these expressions, it's often very hard, and some results were obtained, but not so much from the point of view of quantitatively controlling the objects. Now, the situation gets a bit definitely much better if one simply goes to zero space-time dimensions, because basically, in that case, constructing the zero-dimensional quantum field theory boils down to constructing some random matrix model, and this is extremely well understood on fully rigorous grounds, and many quantities can be studied fully explicitly, quantitatively, and one can prove many interesting results, in particular resulting to the universality property of such models. There is also one case where one can hope to say much more, especially regarding to physically interesting objects as correlation functions, especially beyond the sole perturbative scheme. It's the case where there is one spatial and one time dimension, because in that case, there exists classical integrable field theories. And because of the classical integrability, it's possible to say definitely much more on the quantum quantum variant of those theories. And the way to study those theories wouldn't be precisely through the path integral approach, but more in the spirit of the S-matrix approach. And in particular, those theories, because they are integrable, quantum integrable, they possess an infinite amount of local conserved charges. And while in higher dimension than one, the existence of such local conserved charges other than the energy momentum tensor immediately force the S-matrix of the model to be trivial. In the case of 1 + 1 dimension, this is not the case. And so one is able to construct interacting integrable quantum field theories which have non-trivial S-matrix. So then how would look the whole procedure of constructing such a theory? Well, first, suppose one starts with some partial differential equation for some scalar field phi, which is integrable in the classical sense. So there's a D'Alembert operator acting on phi, and then some potential of the field. And then what one wants to realize is to construct in a way which would be compatible with the expected scattering of the theory. First of all, a Hilbert space on which one would realize the theory. then the S matrix, which would encapsulate all the scattering of the theory you want to describe. So for fixing this S matrix, there are various ways. First of all, it has to satisfy unitarity, crossing symmetries, but also because the theory is integrable, the S matrix has to have the property that
May I ask a question?
Yes.
So this Hilbert space is not the usual Fock space. It's some Hilbert space of interacting theory, right?
Well, in this case, it will be realized. It's realized as a Fock space, and it will be related to how the given S matrix in the theory is described. But even though you realize it as a Fock space, so you could think of it as some space of as some free particle Fock space, you wouldn't have a unitary equivalence on the space between the free theory and the interacting theory you want to construct. But I will then give more details in the Sinh-Gordon case.
Okay.
So how it goes. And so this S matrix has to satisfy rather strong constraints. So this produces a certain classification of possible integrable quantum field theories, which simply result from solving the constraints on the possible S matrices. The input of the S matrix also tells you, in particular, a lot how the Hilbert space of the theory should look like. And once one has the S matrix and the Hilbert space, then one wants to realize on your Hilbert space, well, first of all, the overall symmetry algebra of your theory. So basically the Poincaré group, tell how it will act on this space. Once this is done, then one enters in the interesting part of the construction, because ultimately what one wants is to produce realize certain operators on this Hilbert space, which would depend on the space-time coordinates T and X, and which would kind of lift to the operator level certain classical observables one can have on the classical PDE, like the field or the exponential of the classical field. And one would like those operators to form an algebra in a certain sense. So already here one has to be a bit careful, because these operators, first of all, for various reasons, they have to be unbounded to have something non-trivial, and they have to also be, well, they have to depend. Ideally, one would like to have functions on the space-time which are operator valued, but again, for certain reasons, one need to construct those operators as certain distributions on the space-time, which takes on functions of the space-time, which takes values in unbounded operator. But one way to think about it is just to understand the symbol O of X as the generalized function symbol for the operator O, and so one would like this operator to form an algebra in a certain sense, and this is already a rather non-trivial requirement, because of all the difficulties of multiplying unbounded operators without even thinking about their distributional interpretation. And the second step is once one has these operators, so one wants to have a theory which has the causality property. So one wants if one takes two operators, so 1 or 2, which are local, one wants that these operators commute if they are separated by a space-like interval. So if the Minkowski 2 norm of x minus 1 squared is negative. So this is the first step, but actually, if one wants to apply all this then to physics, or at least to reach physically interesting objects, one should be able to determine in an as explicit way as possible the multi-point correlation functions, which are just taking certain operators you have in your theory, say labeled by some indices alpha 1, alpha n, taking a product of those operators and averaging them over a privileged vector in your space, the vacuum. Actually, all this construction I've listed here, so I've listed it sort of in an operator language, but you can think actually this construction as simply realizing the Wightman axiomatics on the levels of the multi-point correlation functions of your theory.
And can I, for the psi 0, isn't it a vacuum? But if, for example, there's a phase transition, then the vacuum is not unique. So you have, how can you select one vacuum from the theory?
Oh, well, I think in the case of the models, I will be focusing on the definition of the vacuum is clear, because, well, the Hilbert spaces will have a structure of Fock spaces, and the vacuum will be just the vector which has no particles in it, and you at least in the cases I know of, you don't have this problem. But this is also probably related to the fact that these are integrable theories, so they have much more kind of
okay, I see. You're focusing on one super selection sector. I see.
Mm-hmm. And well, once one has done all this construction, then the idea then to kind of say that this construction provides you something consistent with a, say, formal path integral construction, one simply takes these kind of expressions for the multi-point functions, develop them in the coupling constant, and compare with what you would get from formal observation theory. So this is the kind of menu one would like to realize within the bootstrap program. And what I want to describe now is how this kind of menu can be implemented within this bootstrap program in the case of the Sinh-Gordon equation. So first of all, the Sinh-Gordon partial differential equation I've written here. So there's a D'Alembert operator plus mass square over coupling constants times the hyperbolic sine of g times phi equal to 0. This equation is known to be classically integrable. And in the following, it's good actually to rewrite the coupling constant g of this theory in the form of b, which is 1/2 g square over 8 pi plus g square, and takes value between 0 and 1/2 when g ranges from 0 to infinity. So the study of this quantum field theory within the S matrix approach started with the works of Grianic and Vergeles. So they started with the classical model, and using semi-classical quantization, they kind of conjectured on what would be the particle content of the theory, so of the quantum theory. So it should have one particle of mass m, and so they proposed to realize the theory on a Fock-like Hilbert space, which is a direct sum of L-square spaces of Rn with parameters ordered from largest parameter in the first coordinate and smallest in the last coordinate. So at least formally, one can think of elements of this Fock space like incoming asymptotic in-particle wave packets. And again, so using this semi-classical quantization, Grianic and Vergeles argued that the theory has a purely diagonal scattering, and that the scattering, multi-body scattering, is reduced to a process of two-body scatterings, and that the S matrix is just a multiplication by a scalar. And in the rapidity language, the S matrix between two particles takes the following form of a ratio of hyperbolic tangents with zeros slightly shifted in the upper or lower half plane with some parameter depending on the model's coupling constant. So in the bootstrap approach, one simply takes the Hilbert space of the model as this direct sum of Fock spaces, and the S matrix of the theory as the one proposed by Grianic and Vergeles. Okay, and then on this Hilbert space, one wants to implement translation operator, boost operators, and to start with. So if one takes a vector in this Hilbert space, so the translation operator by spacetime coordinate y will act on the vector f Fock component by a Fock component, and if it acts on the n-particle component, it just produces a product of plane waves associated with rapidities, with rapidities beta 1 to beta a appearing in the function times the function. So it acts as a multiplication operator, and here the two momentum of a particle is just m cos beta and sinh beta. And likewise, the boost operator acts component-wise, and boost by rapidity lambda just produces an overall shift of the vector in the function by adding lambda to each of the components. So once the elementary operators are realized, one can ask how one can hope to realize more complicated operators in this space. So first of all, well, how one can represent the action of an operator on the vector of this Fock space. So, well, the operator O acting on F will produce some zero particle space component, n particle space component, and etc. Then if one looks at the n particle space component, well, basically it will decompose linearly as a contribution of O particle component Fm equals from 0 to infinity. And taking each of these Fm's, the operator, there will be an operator acting on these Fm's, which takes L square of Rm and produces a function in L square of Rn. And one wants to have a certain form of translation invariance in the theory. So in particular, local operators, you can realize them by the joint action of the translation operator on an operator.
And the sum over M, does it converge in L2 space?
Yes, so once this is well, in the end, this is something which will have to be checked in the construction. But ideally, of course, the sum has to make sense as producing a vector in L square of Rn for everything here to make sense. So the series should produce a function in L square of Rn. But I will come back to this topic slightly later on. So first of all, I want to just present how one would like to think about constructing operators in this approach. So now basically the construction of operators in this approach boils down to constructing operators which will go from L square of Rm to L square of Rn. And of course, these operators these linear maps would have to satisfy certain properties. But since these are maps between L square spaces, well, one would naturally think about wanting to realize them as certain integral operators. So one may let's focus first on the simplest case. So how would the projection in the zero particle space of the action of an operator or on a vector F look? So according to the previous formula, one would sum up over contributions coming from all Fock components of the Hilbert space. Then each m particle component one would integrate over all the rapidities. There will be some x dependence which just comes from the joint action of the translation operator on the operator one wants to have, and knowing how this operator acts on functions. And then there is an integral kernel of the linear forms one produces in this way. Now, from general principles of at least formal quantum field theory, one should interpret this integral kernel Fm plus as a certain plus boundary value of a meromorphic function of the rapidity variables beta 1 to beta m, which live on a strip of width pi above the real axis. Okay, and then how would look the action of an operator O on an n particle space? Well, roughly similarly. One should act with the operator O on F and produce a function of n variables. So again, we should sum up over all contributions of Fock-Hilbert space sectors. There is a next dependence which come up from this joint action of the translation operator. And then there's an integral kernel acting on the M component function and producing a function of n output variables alpha 1, alpha n. Okay, so this is just, let's say, a way to parameterize the operators one wants to construct. So if one would like to characterize and construct the quantum field of the theories within this formalism, one should be able to compute to provide a description of the integral kernels. So characterize the function dfm of O and the integral kernels mnm of O. And this is where integrability actually kicks in really hard in the construction, because integrability consists then in saying that we will postulate a certain axiomatics in your theory, which will be driven by a S matrix. This is the bootstrap program axioms, and which would correspond in postulating that these quantities Fm and MNM, which will characterize all the quantum fields of the theory, they have to satisfy a certain set of very constraining equations, which you can think of as a certain Riemann-Hilbert problem coupling functions of one variable, two variables, up to n variables, up to infinity, but still scalar functions. And maybe I will not discuss in very big details the meaning of all these equations, but I just want to show these to you. On a very loose formal level of rigor, one could actually see these equations as stemming from the LSZ reduction formalism. But here, within this approach, one should just simply take this as axiomatics, which allow you to fix the operator content of the theory. And then within this operator content, one checks the kind of solvability, well, the fact that in the end, you can get the Wightman axioms working for the theory. So the first axioms of the bootstrap program consists in actually some reduction equation which reduces the number of first type variables in the integral kernels Mn of O. And this basically tells you that if you proceed further and further with this equation, once you know the quantities Fm of O, then you know all the other integral kernels. This is the first axiom. So then you need axioms, equations, which will fix you the remaining pieces of your operators. So these form factor functions, and the first axiom, so this part of the axiom strongly utilizes the S matrix structure of the theory, and in particular that you have factorizability in a two-particle processes. The first property tells you that if you consider these Fn's as certain meromorphic functions in the complex plane, or at least some strip in the complex plane, if you exchange two variables, then you get another form factor, but you have to multiply by the S matrix of the difference of two exchange variables. Then there is some monodromy property. So if you move by 2i pi with one variable, you fall again with the function Fn, but where you have permuted the order of the first variable and moved it to the very end. So already on the level of these equations, the betas are not ordered in decreasing order, but they are to be considered as just generic complex numbers. Then the fourth axiom tells you that there is a certain recursive structure in the Fn's, and it tells you that if you pass from that these Fn's have a certain singularities in the complex plane, which are given by certain simple poles. If two variables coincide up by a distance of I pi, then there is a simple pole, and you have a very explicit form of the residue in terms of form factor with two variables reduced. And also there's an axiom which tells you how the form factors should behave under boosts. So well, one can just start from those equations and then ask oneself what can one say about such equations. And
Karol, so
yes.
can I ask a question? So are these axioms only for this particular Sinh-Gordon quantum field theory, or do they apply to larger class of
Yes.
integrable quantum field theory?
Yes, so they apply to all integrable quantum field theories with certain caveats. So Sinh-Gordon is the simplest one. So it has basically a very simple Fock space which has just one particle. If you already go to Sinh-Gordon, you have even in the, say, simple coupling constant sector of the theory, you have already two kind of flavors for the asymptotic particles, so something like two asymptotic particles. In that case, the S matrix is not scalar anymore, but it's really matrix valued. So the overall structure of the equation stays the same, but you have to take into account that now this form factors, they become vectors, and S matrices become really matrices. So instead of having something like a scalar Riemann-Hilbert problem coupling functions in many variables, you have a matrix valued Riemann-Hilbert problem. But and also in the case of the Sinh-Gordon model, there are certain so-called bound states present, and to take into account the structure of those bound states, which corresponds to certain poles of the S matrix on the imaginary strip. You have to add additional axioms, which tells you, which basically is an extension of axiom 4, which tells you what happens at the poles generated by the S matrix. But this is kind of fully written down. And then for many other models, you already have like this general structure. So structurally speaking, the equation stays the same, but they maybe take a slightly simpler form in the Sinh-Gordon case because of the specificity of the model.
Oh, thank you very much. Yeah.
Okay.
What is the physical reason for monodrome, for the axiom on monodromy?
Actually, so monodromy and pole structure, it's some way to rephrase the causality of the theory. So you use somehow causality of your theory and some calculations you can at least formally do in the LSZ reduction formalism, and then this implies you this monodromy and pole structure. And if you want, the idea here is then to say, I start with monodromy and pole structure for these integral kernels of the operators. And then a posteriori, I will check that if I construct operators in this way, I end up with operators which are causal. Okay, so the study of the bootstrap program was actually, and the formulation of the bootstrap program was initiated by Kozlowski and Weiss in '78. But after very long and huge effort of Fedor Smirnov, it was complemented with additional axioms because Kozlowski-Weiss only wrote a subset of the axioms I showed you. And then Kirillov-Smirnov worked on solving really explicitly these bootstrap program axioms and formulating it in this axiomatic setting I showed you before. And then there is a very long history of solving actually these bootstrap axioms. Many people were involved since the 80s. Various kinds of exact explicit solutions were found in various forms. And now the bottom line is that thanks to this work, there's really a systematic way of solving these bootstrap axioms using the integrability and in particular many fine properties of the S matrix of your theory. And in the end, one obtains really fully explicit expressions for these quantities Fm of O and then for the more general integral kernels coupling m-particle sectors to n-particle sectors. And this is already, in a certain sense, amazing because looking just in the beginning on the coupled Riemann-Hilbert problems, which is given by the bootstrap program axioms, it doesn't look on first sight that one would be able to have such a systematic solutions. So maybe let me discuss the form of solutions you get. The general expressions, so first of all, well, as I said, I will not discuss the multi-point integral kernels because they are just deducibles for the FMs, and it's just a slightly more complicated expressions. But just to give you a flavor, in the case of Sinh-Gordon, the integral kernels for the linear forms producing the zero particle Fox-based contribution of your operator, they take the following form. There's a very simple prefactor given by a double product of functions, explicit functions of a difference of two rapidities, beta A minus beta B. Those functions have a explicit Fourier integral representation. They depend on this coupling constant B, which was a rewriting of the original coupling constants of the classical field theory. And actually, these functions F, you can really think of them as just a solution of the form factor axioms for n equal little n equals to 2 under certain constraint. And then there's a non-trivial part of the form factor, which really depends on the operator you consider. It's given by the K transform of acting on certain functions Pn, which depend on the integration variables you want to have in your theory, beta 1 to beta n, and some auxiliary parameters ln, L1 to Ln, which form vectors whose component takes value in 0 and 1. This Kn transform is given by a combinatorial sum involving these functions Pn, where one sums up over all choices of those vectors Ln with components in 0, 1. There's some sign factor depending on the number of zeros and ones you have in the vector Ln, and then some term which depends on the betas, produces a simple pole at when beta A equals beta B, and vanishes if the components La and Ln are equal. And one should act with this Kn transform on a function Pn of O, which fixes the operator O on which one acts. And the whole point of this kind of rewriting of the answer is that the equations for the Pns of the operator are extremely simple, much simpler than the form factor axioms, and you can just try to produce solutions by hand. So many operators were constructed explicitly with explicit expressions for the Pns of O's. I will not discuss the explicit expressions for the Pns because they're a bit bulky in most cases, but for instance, for the exponential of the gamma times the field operator, you have a full expressions for the Pn, for energy momentum tensor, for currents, and for various descendants of the exponential of the gamma times the field. You also have some predictions for the Pns. Okay, so in this list of construction I've shown you before, so far what was achieved is that one takes a certain form of the Hilbert space, a certain form of the S matrix, then tells how one realized the symmetry algebra on this Hilbert space, and produces local operators as certain integral operators, and it gives a closed expression for their kernels. So what remains? So and this is precisely the question about that say the action of the sum of those operators O and M on the function F should produce some object in L square in the appropriate L square space. So what you want to have first is that you want to be able to multiply them, the operators in a certain sense. So the operators, so you want to check that they satisfy an algebra, and this is already very non-trivial property, or if you want, constraint on all the integral kernels of the operators. Then you want to check that the operators you construct in this way will produce a causal theory. And finally, you want to compute the multi-point correlation functions and have closed expressions for them. So let's first assume that the algebra question is resolved. We can multiply the operators, and let's look what one would get for the multi-point correlation functions. So immediately, by just massaging up all the formalism I shown you, if you want to compute a multi-point function of, say, a product of some operators at space-time t and x and space-time position 0, 0, averaged in the vacuum, one gets the answer in the form of a certain series of over n of n-fold integral, where the integration runs over Rn, and one integrates those form factors which solve the bootstrap program axioms, and weight it with some terms which decay with the distance, and this is in the case of space-like interval separation between the operator. So here everything is explicit. The one just can substitute the expression for the fn's which I've shown you before. One gets a double product of functions f, and then some square of the kn transform function weighted by some quantity which decays faster than any exponential at infinity. Of course, now the delicate point in this at this stage is that somehow, well, knowing that there is the algebra structure for your operators, and somehow this implies you already that this series is convergent. But in principle, this is something which still remains to be tested and established. And in a certain sense, it's fully proving convergence of such series or more complicated series for multi-point functions is equivalent to having in the end the algebra structure. But still, if one assumes the algebra structure, what one can do, well, one can try to write the commutator of two operators just by looking at the integral kernel of the commutator. It will still be given by certain series of multiple integrals. And then Kirillov-Smirnov, by assuming that those series converge, they showed that the input of the form factor axioms, when written down on the level of the series you obtain, you can do several manipulations with the series in such a way that you have cancellations if your operators are separated by space-like interval, and you have causality. So under the hypothesis of convergence of all the operator products in series resulting from them, the bootstrap program axioms guarantee you causality. And then again, just to flash rapidly to show you that you can compute multi-point correlation functions in this theory. So in the case of two-point functions, it was the calculations are very direct, and it was known. I guess it goes back to early works of Zamolodchikov and Smirnov on the subject. The case of multi-point functions was not really considered in the literature on explicit level, but with Poteau we obtained some closed expressions. So again, assuming that all kind of operator products work very well and are well defined, then the multi-point function, you can write them in terms of very explicit series of multiple integrals over certain contours living in the complex plane. The contours depend on whether the points xa and xb are space-like or time-like separated, and everything is weighted by some form factors fn of the operators, or you consider in your multi-point function, evaluate at the appropriate point in the complex plane. So the bottom line of this formula is maybe not so much to read, but if one wants to have an explicit expression and then hope to draw some informations out of it, then it's fully possible, because all constituents in this formula are fully explicit. But now comes the last question, which was open for a very long time in this whole construction, is can one verify? Yes, maybe, and I can comment on the level of this formula. So actually, if you have convergence of this kind of series of multiple integrals, then you can just simply say that, well, I define my theory in terms of its multi-point functions. So I just take this expression for L-point functions, and I check that it satisfies all the Wightman axioms. And because of the way the theory was constructed, you exactly get that you satisfy all the Wightman axioms. So up to the question of convergence of those series, everything works fine. But the convergence was open for a very long time because the integrands in these multiple integrals are very rather intricate, and so it's difficult to make direct bounds. First of all, there is a class of multiple integrals which are very well understood from the point of view of convergence. These are the classes of series of multiple integrals which are related to Fredholm determinants. So basically, by definition, a Fredholm determinant would be of some operator identity plus k, with k compact trace class operator, say acting on L square of C, where C is some curve in the complex plane which is compact. The Fredholm determinant is just given by a series of coefficients Gn, where Gn is an n-fold integral over this contour Cn of 1 over n factorial times the determinant of the integral kernel of your integral operator, evaluated at integration variables beta a and beta b. And because you have Hadamard bounds on the determinant of any matrix, you can apply those bounds here and use that you have a 1 over n factorial term here to kill the n to the n over 2 growth of the Hadamard bound to see that Gn actually decays extremely fast with n, so you have a quickly convergent series. But the reason why one can do such bounds stems really from the presence of from the possibility to write the integrand as a sole determinant, and the fine cancellations implied by the determinantal structure of the integrand are partly responsible for the Hadamard estimates. But in the general case of, say, the series I've shown you here, this is not the case. You cannot write them in the form of a Fredholm determinant. And so you have to rely on very different kind of bounds. And in fact, even in the Fredholm determinant case, if you would not have Hadamard bound, and maybe if you would forget about the spectral interpretation of a Fredholm determinant, then the estimation of the growth in n of the convergence of the series would be an equally complicated problem. Up to recently, actually, the only proof of convergence of such series of multiple integrals which describe correlation functions in some quantum integrable theory, which is truly interacting, were due to Fedor Smirnov in the early 90s, and he did it for the Li-Yang quantum field theory. And Sinh-Gordon is slightly more general. Is definitely more general in this case. The caveat of Smirnov's approach was that it was extremely specific to the very fine details of the representation you have for the form factors in the model. So there was no chance absolutely to pass on his estimates to more complicated models. And this was kind of the challenge was to devise some effective techniques to prove the convergence. So what was the problem, the remaining problem at stake, at least in the case of 2-point functions? So in that case, if one goes back to the 2-point function I showed you here, we have a series of n-fold integrals. And then if I write those n-fold integrals explicitly, what I would get is the following n-fold integral, which depends on two parameters r and alpha. So the integral goes over Rn. There's this exponential of minus r cosine and hyperbolic cosine and sine terms, which ensures a very fast decay of the integrand at infinity. Then there is a part e to the 1/2 w of beta a minus beta b. This is just exactly the rewriting of this product A different from B of this involving the function f, but doing it in a more symmetrized way. So anyway, the two-body interaction in this multiple integral is fully explicit, given in terms of a Fourier transform. And typically, if you it depends on the coupling constant B of your theory, and if you vary the constant B, typically you get this kind of plot for the two-body interaction. So in particular, it goes to minus infinity when its variable lambda goes to 0 as log two times log of the absolute value of lambda. And in this multiple integral, you have a last term, which is this Kn transform of some function Pn squared. And I remind you here the expression of this Kn transform, so some combinatorial expression involving the Pn functions, which depend on some general operator. So maybe here I can already discuss a bit more precisely why the integral is already well defined. Well, first of all, for reasonable class of Pns, and definitely all the Pns which will give rise to some operators on your field theory side, Kn of Pn will not grow very fast. Maybe the fastest growth would be like exponential of variable beta a to power k. Because of the shape which I plotted for W, e to the half of W is absolutely bounded function on R to the n if we take the double product. Moreover, you see that the Kn transforms, they induce a certain poles, simple poles at beta a equals beta b. So because you have a square, you have double poles at beta a equals beta b. But the double poles are simply cancelled by the logarithmic singularity at the origin of W function. So everything is regular. And then the convergence at infinity is guaranteed by this exponential factor in the one-body interaction. And then the theorem one can prove is that if one assumes that the functions Pn have a certain uniform in n bound of the following type, there is a certain constant C1 which you can raise to power n times exponent of C2 times beta a to power k, and we take the product over all beta a's. So if there are some constants C1, C2 which do not depend on n, and a constant k also not depending on n, such that you have such a bound, and this is definitely satisfied for all operators, all p's which will give rise to operators of interest in your theory, then the series of these multiple integrals with summand un of r and alpha will converge uniformly when the parameter kappa, which is the combination of r times 1 minus absolute value of alpha. So r is the prefactor in the exponential and alpha is the prefactor in the sinh. The series would converge uniformly whenever this parameter kappa is uniformly away from 0 up to kappa equal plus infinity. And you have explicit upper bounds on the growth with n of this un of r and alpha. It goes slightly sub-Gaussianly, like some explicit constant which depend on the coupling constants in your theory, minus 3/4 of pi to the fourth b hat, so b hat is half minus b, times n square divided by log n to the cube, and then you have corrections 1 over log to the n, 1 over log n. So first of all, one could think that because there's no Rn alpha dependence in the leading term of the upper bound, then the result should hold up to R tending to 0. But actually there is the control on the remainder is not uniform in alpha. And in particular, the remainder will become more and more important if R goes to 0. And this is as it should be, because one expects that two-point functions, if one takes the series un of R and alpha and specialize to a two-point function in the Sinh-Gordon model, then one expects some universality to pop out in the short distance limit. And in particular, the series should exhibit a power law behavior in R, which is non-compatible with convergence in the R going to 0 limit. So this is fine. And the second point is that the K is slightly sub-Gaussian. So it means that the 1 over n factorial term actually is totally irrelevant for the convergence. It was a bit misleading when I showed you the Hadamard bound, that the 1 over n factorial in front of the multiple integral was saving the day, but actually the integral, the n-fold integral, either goes to 0 much faster than 1 over n factorial or blows up much faster. And so this result allows you to show that several things. So first of all, you can show that in the form factor expansion, so the expansions I've written you for two-point function, which are space-like separated, are well defined. It also shows you that actually the series I've written down for these multi-point functions, whenever the space-like distance is finite, it converges extremely fast because terms decay slightly sub-Gaussianly, and this was observed numerically a long time ago. So somehow this confirms these numerics also. Then a rather direct modification of this, the proof for the n-fold integral will work to show you that you can that the operators form an algebra and that they are well defined. So in particular, this allows you to finish the proof of the local commutativity theorem of Smirnov and Kirillov, which was relying on the convergence hypothesis. Now, this is established, but still, to kind of wrap up the construction, one needs to have to show the convergence in the time-like regime. This has not been done yet. It's doable, but it's more technical. And then one should also prove the convergence for multi-point functions, because one can show that the operators will form an algebra, so produce an operator, but then still one wants to show also that one can kind of take products of many operators, or that the expression I show you for multi-point function is convergence. And once this is done, then the full construction of the theory is done with immediately the input that you have closed explicit expressions for the correlations from which you can study, say, UV universality, so short distance behavior of correlators by using their explicit expressions, and hope to say something about this universal behavior, which should be grasped by certain conformal field theory. But also you can give very precise bounds, say, on the large distance asymptotics simply by studying elements of this series. And maybe it's time to conclude, so I would not really have time to discuss how one can analyze such n-fold integrals, but this is maybe already more on the technical side. But basically the idea is that you can at least think of those integrals as some complicated cousins of the integrals, n-fold integrals, which arise in the study of certain ensembles of random matrices. There were many methods developed to study the large n behavior of such integrals by many people since the I think early 90s up to 2010, and then one needs to kind of improve those techniques to be able to deal with more complicated n-fold integrals. This can be done. I'm skipping the details, and just let me conclude. So basically, well, what I presented you was just one way to formulate an integrable quantum field theory through the bootstrap axiom. And I showed you what can be solved in this, how these bootstrap axioms can be solved. And basically this led to the last kind of open question in this construction to make it fully rigorous, which was related to convergence of series of multiple integrals. So in simplest cases, it was already the method was set up and it looks sufficiently robust and model independent to apply it to many other cases. Some technical input has to be put in the method on top of what was done for random matrices for the method to work. And then what would be interesting would be to finally prove convergence of multi-point function. This is under investigation, and then apply to more complicated integrable QFTs like Sinh-Gordon. So thank you for your attention.
Thank you very much. Thank you for the very nice talk. Okay, are there any questions, comments? Okay, Łukasz? Please go ahead.
Thank you very much. Do you hear me now?
Yes, yes.
Yes, we can hear you.
Thank you very much for a very interesting talk. I have two questions. The first one is about the bootstrap axioms. Namely, it so happens that I deal with physics, but also with mathematical logic. So if a logician hears about the axioms, he very often associates this with a formal system. A formal system, for example, system of arithmetic, when you have the set of axioms and the set of rules, inference rule. My question is such, whether someone went into the more formal direction by considering the axioms, for example, bootstrap axioms, and the rule of inference, for example, modus ponens rule, generalization rule, and so forth. And this is one question. And second question is such that, as this is very well known fact, there is an equivalence of Sinh-Gordon model and massive Turing model. Yes, my question is about whether is there any analogy to this case when we say about sinus hyperbolica Gordon model, namely whether there is an equivalence of this model with any other massive model, for example, as in that situation, that Sinh-Gordon model and Turing model. Yes. So this is such issue.
Oh, okay. So well, regarding to the first question, I don't know if somebody push kind of the axiomatic these axioms kind of in the direction you mentioned. So I cannot answer more. But regarding to the second question, so definitely the Sinh-Gordon model. Well, if you go to the Sinh-Gordon model, the kind of particle content of your theory would depend on the coupling constant. So there is a regime of a coupling constant of a theory where you have particles which we would call soliton and anti-soliton. And then if you move in the coupling constant, you start to see some pores in the S matrix appearing in the S matrix, and you start to add new kind of particles to your theory for the theory to make sense, or if you want to be causal. And these particles, you call them breeders. And the Sinh-Gordon model explicitly will be equivalent up to some simple transformations to the breeder sector of Sinh-Gordon theory. So if you would just kind of cut the Sinh-Gordon theory and just limit it to one breeder sector, then you would have kind of correspondence of the expressions for the operators in those.
Okay.
But this is the only equivalence I would know of.
Yes, many thanks. Thank you very much.
Okay, any more questions? So you can just unmute yourself and ask.
No, Kasia, there are two raised hands. And first is,
I
think
didn't
Yo's
see
hand.
them. Yeah, sorry.
Yo first, I think.
Oh yeah, Yo.
Thanks. Thanks for the talk. Do you hear me?
Yes.
Okay. I'd like to ask the status of the Wightman axioms. Do I understand correct that if you also put a convergence for the time-like distance on the multiple particle part, then you will get the Wightman function? Is that correct?
Yes.
Okay.
Yes.
Thank you.
Okay, and the next is Patrick.
Hi, yeah. Could you say some more about this when R gets very small? Can you make any progress on resumming to see things like scaling dimensions of the operators in that limit?
I've made some attempts, and there was some small progress, but it's definitely still, I would say, very far away from something kind of tangible in that case. Small asymptotic analysis of those series is yeah, there are many problems appears. You can start to see some indications that there would be some power law behavior, but there's still not, I wouldn't call it a good control on the constants arising there and all that.
I have some vague memory that Jean-Michel Maillet and co in the lattice context had made some progress in the last few years. Is there some way to relate their work to yours, or?
No. Well, so in the lattice context, like the short R behavior would correspond to large distance behavior on the lattice.
That's right,
would
yeah.
consider XXZ chain or things like this. So definitely, well, the methods I tried applying the methods we developed with Jean-Michel for dealing with the lattice cases, and so some parts of these methods work, but there's some more to be added to this, and this is what is blocking for the moment. So for the time being, I'm starting to see some indications that there would be a power law behavior, but there's not enough control yet on everything to.
Okay, thank you.
Okay, Wojciech?
Yes, so can you hear me?
Yes.
Okay, so I would have maybe more a historical question. How people actually guessed the two-body scattering matrices for Sinh-Gordon and other factorizing models?
Okay, so I think the story started really with Sinh-Gordon, and with Sinh-Gordon it was semi-classical quantization calculation. So they were starting with the classical Sinh-Gordon theory, for which they can Vergeles and Brianik, for which they can compute everything they want, and they were computing order by order. Well, the S matrix order by order and perturbation around the classical theory. And then they started to see that actually the expansion looks like expanding this S matrix in powers of B, around B equals to 0. Like, well, they compute first, second, third order. So then they kind of guessed that this formula should give the expansion. But then once you have this formula, you can start to say, well, okay, but so I have a theory which has one particle, only one asymptotic particle content in terms of construction of the Fock space, and I should have only purely diagonal scattering. So then the S matrix, well, it's diagonal, it has to satisfy unitarity and crossing. And this provides some equations on actually the full possible form of S. And then you can see that this case is actually one of the solution of unitarity and crossing, and you can list all possible other solutions. So it's basically you add more zeros and poles to the S matrix if you want something more complicated. This is how it started. Okay, and then people started to think, well, that on the level of the classical theory, what makes the theory actually integrable is that you have an infinite tower of local conserved charges expressed in terms of fields or momenta of your theory. So the idea was that actually, and this is what Brianik and Vergeles were the first to argue, that on the quantum level, you should have something of this sort as well. So a full additional tower of conserved charges in your theory. And then other people started to argue, well, then, oh, okay, but then this means that even if you have a complicated particle content, because you have many conserved quantities, basically this implies that you have only that n-body scattering factorizes into two-body scattering processes. This was, I think, Parke and some other person argued that. And then it was kind of rigorously formalized by Jagolnice within his S-matrix approach of quantum field theory. And if you have all that, basically, and this is also an observation of Zamolodchikov, then even if you have a more complicated theory than Sinh-Gordon, the S matrix has to satisfy a certain consistency equation in order for the factorization of n-body scattering into two-body processes. And this is called the Yang-Baxter equation. And so then for more complicated theories, what you actually do, you start with the Yang-Baxter equation and you look for certain matrix solutions to the Yang-Baxter equation, which satisfy unitarity, crossing, and maybe other symmetries you want to have in your theory. And then you have like a explicit kind of classification problem. In principle, when you find a solution to the Yang-Baxter equation and all other equations, you have a candidate for an S matrix of a quantum field theory. And then, for instance, you can perturbatively check in the coupling constant that by doing semi-classical calculations on the classical integrable model of this associated to the quantum field theory, you get some coincidence of expressions. And actually, you can even nowadays consider the Yang-Baxter equation on purely representation theoretic level, and then produce systematically using representation theory a large amount of solutions for S matrices. So this is how it historically went. After the inputs of Granic and Verkeles, there were many inputs of the Zamolodchikov brothers and Fateyev and a few other people. Now I missed the name who produced systematically these S matrices by solving the Yang-Baxter equation.
Is there some I don't know, textbook review of it, or is it all like scattered in the literature, half pre-electronic?
I would say, well, there are some review papers. I think there's one review paper by Patrick Dory. There's one review by Jacob Bombardelli and one by Benjamin Doyon on some aspects of this, which touch especially the S matrix part. And then there is the book of Fedor Smirnov, which discusses construction of form factors for the Sinh-Gordon model.
Okay, I see. Okay, thank you very much.
Thank you for this very nice historical review. I mean, this is very useful. And anybody else? Any more questions?
May I ask? If one replaces the Minkowski space, 1+1 dimensional Minkowski space with the Euclidean space, does it help? Does it help, or the story is the same?
Oh, the story is the same, because actually, well, I completely skipped this part because it's a bit technical. But the one of the points is that, well, you still have to consider operators you construct in this way, where I was writing them in terms of their generalized symbol. You still have to consider them as distributions. So actually, when you start to compute a multi-point correlation function, you should write it in a distributional sense, and then to write it as bona fide functions on the spacetime, which was the presentation I showed you before, you have to do a certain amount of transformations on your integral representation for the multi-point function. And once you do, well, using the regularization provided by the distributional way you write it up, and once you do all that, basically what you see is that you move from Minkowski spacetime to Euclidean spacetime in terms of the time. It's as if you would do a Wick rotation of the time, and this produces already this fastly convergent terms. So in this sense, you have really full equivalence of Euclidean and Minkowski formulation of your theory. Kind of the Euclidean formulation would immediately give you well-defined kind of operators, whereas the Minkowski one, you have to start with the distributional regularization, well, distributional interpretation of your operator, and then do some handlings to make it well-defined, and just see that what was a priori distributions are actually realized as function, except when you are on the null spacetime distance where things happen.
And what about the conformal invariance? So these models are not typically conformally.
No. So this model, you can think of them as certain perturbation of conformal field theory. I mean, in the Sinh-Gordon, I think you can think them as perturbation of Duvel CFT. And what happens is that actually, when you compute, say, correlation functions, multi-point functions in this theory, and you consider multi-point function in the space-like regime and take short space-like interval limits of those correlation functions. So effectively speaking, you fall into a spectrum of a conformal fit theory if you would look at which part of the spectrum of your theory should contribute to the correlation function. And effectively speaking, so you expect that this short spacetime distance asymptotics of your two or multi-point correlation function should exactly coincide with multi-point functions you would compute in CFT grasping this limit. So this is how CFT would pop up from these models, but so far it was just like done only on like hand waving level arguments.
Nice. Patrick has another question.
Yeah, just to follow up actually. So I know people have also proposed massless S matrices corresponding to theories which are also conformal in the infrared. Now, one would guess that, and somehow surprisingly, form factors seem to converge in those cases too, because naively you would assume that the convergence was much more difficult. Did you ever think about proving things for those theories?
No. I didn't look at all at that.
I'm curious as to whether what you're doing would also work in those cases.
Okay. And any more questions, comments? So I have a question / comment. So yeah, this is very nice. I really like this. So I have a paper with my collaborator Dorothea Bans on the construction of Sinh-Gordon, actually in 1+1 Minkowski. And so our proof is based on estimates on time-ordered products of fields. And it looks very much in a similar style to what you have done here. So I was wondering if there is a connection, like can one maybe use similar methods? So we were coming more from, well,
so you were using more like cluster expansions and techniques of constructive renormalization.
That as well, but in a later paper. So originally we were just looking at, okay, so define the S matrix very naively, like the exponential in time-ordered products, and then you can estimate these time-ordered products. Well, using very similar things as you did. So you have the explicit expansion. Well, you have explicit expression for the Feynman propagator, which is like essentially a log, and then you have powers which you estimate using like a Cauchy determinant. So yeah, and then we show like the convergence of the series at the end. But yeah, so that worked for Sinh-Gordon, but the similar thing wouldn't work for Sinh-Gordon for us, because then we wouldn't have that sort of Cauchy determinant formula. So but you have like very strong results here. So yeah, maybe there's some
Well, there's definitely a parallel with the Cauchy determinant, because what makes these multiple integrals deal with convergence is that, well, you don't have a Cauchy determinant present, but in a Cauchy determinant, the Cauchy determinant vanishes when two variables come close to each other, and you have sort of similar effects under the integral, and then you can kind of deal with all that using some tools from potential theory. And
so if you were doing Sinh-Gordon, as you said, you would. Is this the method you would be using as well, like Cauchy determinants and this kind of stuff, or do you have a different?
Maybe not. Well, you don't get explicitly Cauchy determinants, but well, the similar kind of bounds which appeared in this multiple integral would definitely appear in Sinh-Gordon, but just the functional content of the integrand would be more complicated. And basically, well, the whole procedure here is basically, well, one reduces the computation of the upper bound for the integral to finding the infimum of a certain functional on some auxiliary space of probability measures.
Yeah, this is nice. and yeah, so I work in Lorentzian signature, so it's really nice to see something which works so well in Lorentzian as well as Euclidean. So and there is a sort of synergy between those. So yeah, I definitely have to look at it in more detail. Yeah, thank you. And any more questions? Okay, so I think we're done. So thank you very much for the lovely talk, and I think that's the time to close.
Thank you very much.